Alright, so welcome to my awesome chemistry channel that I just started right now. It's actually a joke. I don't have a chemistry channel, but I told my sister that I would record a video to show her exactly what I'm working on in chemistry and what I think I know about chemistry so far. So anyway, what I'm going to be talking about is a chemical reaction, and what it starts with and then what it ends with. Basically, whenever you mix aluminum sulfide with water, it goes through a chemical reaction and becomes aluminum hydroxide, and it also becomes hydrogen sulfide. Well, hydrogen sulfide, I guess, is like the byproduct. If you were trying to make aluminum hydroxide, you could do it by mixing these two. You get a little runoff of hydrogen sulfide, or maybe that's what you're trying to make, and the byproduct is aluminum hydroxide. Either way, you start with two ingredients, and it becomes two ingredients. So the first thing that you have to do is decide what the chemical formulas are for these different descriptions. Aluminum sulfide obviously is going to have aluminum and sulfur in it. So we know it's got aluminum and we know it has sulfur. Um, so the first thing that you have to do with this is you have to kind of balance the molecule itself. And to do that, you need a periodic table. Oh, shoot. I get my computer to open my periodic table here. So aluminum, based on its position, we know that it's going to uh, no, it's going to lose 3 electrons. So aluminum by itself will lose, um, yeah, it will lose 3 electrons. So it is 3 positive. Sulfur, based on its location on the periodic table, because they're all kind of grouped together. So if you know the groupings, then you know how many electrons they will lose or gain. And by that electron exchange is what makes these ionic bonds that connect everything. So the aluminum and sulfur will actually lose 2. So these two things do attract, but they are not balanced. So you'll need more than one of each to make this work. Now, because 3 and 2, the lowest common multiple is going to be 6, because 3 goes into 6, 2 goes into 6. So if you say aluminum is, if you have 2 aluminums and 3 sulfur, that will balance the electrons. And so then you get aluminum sulfide is going to be aluminum with sulfur. The suffix "ide" means that that's alone. There's no oxygen or anything like that present. So you got aluminum and sulfur. Aluminum sulfide is what that becomes. Water, much easier. Everybody knows water. Hey Liz, can you not tinkle in my video? Thanks. It's okay. It's my wife in the background. Anyway, water is H2O. Everybody knows water, very common, but that one, we're just going to go ahead and call that one balanced because everybody knows that water is H2O. But as you might imagine, hydrogen will gain or lose 1, and oxygen will, they'll gain 2. So in this case, hydrogen is losing 2, oxygen is gaining 2, and that's how that becomes balanced. You got aluminum again on the other side. We're just coming up with the chemical formulas for this, but this is basically going to be aluminum sulfide plus water reacts to become aluminum hydroxide. So you got aluminum. Obviously, this time you have hydrogen, and you also have oxygen, the oxide there. So with aluminum, oxygen, hydrogen, aluminum we know loses, or no, what is it? It loses 3. So I'm going to go ahead and save balancing on this one here. The aluminum will lose 3, H2O, or I mean H and O. In this case, actually, the H is going to gain. Well, I'm actually just going to save that and say that it is aluminum HO3. I already looked up the chemical formula. You can balance it using the periodic table, but that's not really the point of this video, and we've got a lot to cover. So with hydrogen sulfide, you know that hydrogen will gain or lose 1, and sulfur will gain 2. So in this case, hydrogen is losing 2, and the sulfur is just 1 present. So, and again with the "ide" suffix, meaning that it is solo, no mixture of different stuff. So now we've got our chemical formula, or at least the chemical names to represent what's happening in this chemical reaction. Aluminum sulfide with water will chemically react and create aluminum hydroxide and hydrogen sulfide. So that's the first step, but we're still not done with this equation, because everything that goes in on this side has to come out on that side, and that's because of the laws of thermodynamics. There is no you can't lose you can't lose energy, you can't gain energy. Like, whatever energy goes into a system has to come out of a system. You can't create or destroy energy, and likewise you can't create or destroy matter. So every element that goes into this is going to come out of this, but rearranged differently, and that's what happens during the chemical reaction. So for this, we know that, basically you just kind of go through it. You've got 2 aluminum on this side. You've got 1 aluminum on this side. So you know automatically you're going to need at least 2 of those, because you need 2 aluminums to balance this on this side. So then that's going to make twice as many hydrogen and oxygen, because twice as many. And you've already got 3 of those, because there's a little 3 suffix outside of this parenthesis. So now you've got a total of 6 hydrogen and 6 oxygen here. Hydrogen, oxygen here, you've only got, you've got 6 hydrogen here, and you've got 2 more here. So really you've got 8 hydrogen over here. So let's see, that's 6. Yeah, 6, 8. It's still not quite balanced, but let's not worry about hydrogen right now, because honestly hydrogen is present in both of the resultants, and you kind of want to stick with just, you want to start with the ones that are not balanced. So aluminum is now balanced. We're good on aluminum. We've got 3 sulfurs, and sulfur only goes into one of the resulting molecules. So let's go with that. Okay, we've got 3 sulfur on this side, only 1 sulfur on this side. So we're going to need at least 3 of those. Now this is kind of a process, and you can do it different ways. A lot of times stuff is pretty easy to balance. You can just kind of go this method. But now let's take a look here, because we've got H2O. We've only got 2 hydrogens on this side. We've got 1 oxygen, but here we've got 3 oxygen. So we know there's got to be at least, no, we've got more than that. We've got 6 oxygen, because that's 2 times 3, 6 oxygen. So let's say this is the only oxygen that we have on this side. So let's say we have 6 molecules of water. So now what does that do? We already know this is balanced for now. We've got 6 times 2 hydrogen, which is 12. We've got 12 hydrogen. That's 6 hydrogen right there, because 2 times 3 is 6. 6 hydrogen. Over here we've got another 6. That's 2 times 3. So that's another 6. That's 12. That balances. Right? Yeah, because we've got 6 times 2. So we've got 12. So that actually balances. Our hydrogen is now balanced. Oxygen, we've got 6 of them. That's 3 of them right there, times another 2. That's 6. So I think everything balances. And if you want to check that, you can actually just draw your little 4 here. Maybe it's 4. Let's check. It's aluminum, sulfur, hydrogen, oxygen. That's all the components of this. Of the aluminum, we have 2 on this side. We have 3 sulfur. We've got 12 hydrogen, and we've got 6 oxygen. And all I'm doing is multiplying by the coefficient or the suffix to make that number there. So on this side, we've got 2 times aluminum. We don't have aluminum anywhere else, so that's 2 on this side. 3, we've got 3 sulfur on that side. On sulfur on this side, we've got sulfur times 3, so that's good. That balances. Hydrogen, We know our hydrogen balance, but let's go ahead. 12 plus hydrogen times 3 times 2 is 6, plus 6 more hydrogen is going to give us 12. That's 12 hydrogen. Oxygen, we've got 3 oxygen here times 2 is going to be 6. Looks like that checks out, so that's all good. So now we've got our balanced equation, and that equation is 1 aluminum sulfide plus 6 water molecules will react to become 2 aluminum hydroxides plus 3 hydrogen sulfides. So now we also, with this, you want to go ahead and realize that you've got a ratio here. That's 1 to 6 becomes 2 to 3. That's going to be important later. So, you just want to go ahead and point that out. Just kind of recognize that if you have 1 aluminum sulfide, you're going to have 6 water, and that's the exact measurement of these molecules that are going to react with each other. And later on, we'll talk about how it works if you have a certain number of grams of this material, and you combine the two. What's going to be left over, because there's always going to be a little bit left over, because no typical instruments are not going to measure to the atom, and that's what we're working with here. Is these are atoms and very, very, very tiny things that are reacting with each other. So yeah, that is our that's the way that we're going to describe our chemical reaction that's happening. So the first thing we want to know, and actually we're just going to jump right into it. If you had 20 grams of aluminum sulfide, okay, so we'll say we have that many aluminum sulfide. We've got 20 grams of it, and we're going to mix that with 20 grams of water. Now, grams is a weight. Let's call that H2O just to keep everything consistent. Grams is a weight, so it would be difficult to throw water on a scale, but obviously you put in a container, measure the difference, and you come up with a gram weight of that, and that's going to be what those things weigh. Yeah, or mass. Yeah, I think it's weight. Well, I mean weight, mass, it's all the same. Like, you can figure it out. So anyway. What we need to first do to figure out how this is going to react whenever we put it into our chemical reaction. So obviously 20 grams of aluminum sulfide and 20 grams of water, it's not going to balance perfectly. With this chemical reaction, we've got a 1 to 6 ratio, so maybe some more of the water is going to react with the aluminum sulfide. One of them is entirely used up, and the other one there's going to be a little bit of leftover. It's called a limiting reactant. So we need to find out which one that is. And there's different ways of doing this, to figure it out. But the best method that I have found, because there are different methods. We're going to use the atomic weight of different things, and we're also going to convert everything into moles. Moles is going to be a very important measurement. It's a number basically, but whenever you're dealing with atoms, you're going to have so many atoms in a gram. It doesn't make sense to list it by atoms. Even using scientific notation, you're going to end up with huge exponents, and it just doesn't make any sense. So they created a number, and it's 1 mole is going to be equal to 6.022 times 10 to the 23rd atoms. Now that's a number to number ratio. So that, literally, this is not necessarily a unit conversion. You're not converting anything. You're just saying this is a preset number that is equal to that many atoms, and they call it a mole. So anyway, that's a unit conversion that you absolutely have to use for dealing with atoms. So we're going to remember that. So the first thing that we want to do is we're going to build a little table here, okay? And our table is going to be basically like, at the start, how much of this particular uh, atom, how many molecules do we have of that, and how many moles of atoms or how many moles of molecules do we have of that particular thing at the start, and then we're going to do like a plus minus, which is going to tell us how much we gain or lose, and then at the end, how much we have of each. And we'll break that into our four little components, Al2S3. You want to add the coefficients in here too. It's not going to be super relevant right away, but it will just remind us that we have that what do you call it? That ratio of how things should match up. So it's good to have that in your table. So that's our H2O. Now we're going to go ahead and add our aluminum hydroxide, which we have a 2 ratio of that. Aluminum OH3. And last, we have 3 hydrogen sulfides, H2S. Okay, so our table is not going to be in grams. Like that's what our weight is here. So we need to figure out how many atoms we have. We don't want to know how many grams we have because all of these different atoms weigh different things. So, saying 20 grams of water, it's not the same. It's not going to be the exact same amount of atoms that we have in 20 grams of aluminum sulfide. It's just not. They weigh different things. They're different sizes. Like the different elements. They're completely different. So you can't say that 20 grams. I mean, 20 grams is equal to 20 grams as far as they weigh, but that's not going to be the same number of atoms. So we got to figure out how many atoms are in there, and we're going to do that in moles, not atoms. But that's the same thing. It's an equivalent. But we're going to use moles because it's an easier number to work with than these super high exponent scientific notation numbers. So, anywho, let's get to it. So first off, we're going to need to figure out how many mole of aluminum sulfide we have in 20 grams. So this is seriously the most basic unit conversions that you can do. 20.0 grams times, and we're working with our aluminum sulfide first. Sulfide, sorry, aluminum sulfide. Now, we know we want a mole and we want to get rid of our grams. But how many grams, no, how many atoms are in this? So, like, how do we figure that out? Well, it's actually pretty easy. What you would do at this point is you take the different elements that you have in here, aluminum and sulfur, and you're going to take the little suffixes, and you've got 2 aluminum, 3 sulfur, and you're going to multiply that by the atomic mass that you get from the periodic table. So aluminum has an atomic mass of 26.9815. That'll be good enough, close enough for what we're doing here. So 26.9815, 26.9815. And sulfur is 32.059. 32.059. Okay. So now we know what that is going to weigh, and if you calculate those out, and again, these numbers come from the periodic table. Any periodic table that has the atomic mass listed on it, most of them do. That's where these come from. The suffixes come from our. Go back to the video so I can see what I'm pointing at here. It comes from our suffixes. Like that's where these come from. So like this is not a complicated thing that we're doing here, but we need to know what the entire atomic mass is of that molecule. So whenever you add these together, you come up with roughly, very close to 150.14 is the total atomic mass. Now, the important thing about that is that that's an AMU. That's atomic mass units. But we can't use AMU. The great thing about chemistry and the great thing about this design is that 150.14 AMU is exactly equal to how many grams per mole that particular molecule has. And that goes for all the molecules, all the elements. You can figure out the atomic mass, you can figure out the grams per mole. So now we've got a grams per mole comparison. So we can say this is 1 mole per 150.14 grams. We run that through. That's going to give us 0.13321 mole of aluminum sulfide. So that's how much we start with in our aluminum sulfide. Oh, I kind of made that ugly, didn't I? Let me fix that. Just move that down a little bit so we can have an actual table, plus, minus, end. Okay, so we are starting with 0.13321 mole, 0.13321 mole of aluminum sulfide. Now we need to find out how much water there is, obviously. So same process. We've got 20 grams of H2O. I won't go through the whole process there again, but I can tell you that the atomic weight of one molecule of water is 18.02, and you would do that obviously by just figuring out the hydrogen and oxygen in the same way that we did the aluminum sulfide. So once you have that, you run that through, and that's going to give you 1.1099 mole of H2O, of water. So that's how much we start with here, 1.1099 mole. So now the thing that we have here, this is, after this stage, everything else becomes super easy, because what we need to know is if this is a 1:6 ratio, because this should be, because one of these molecules will react with 6 of these molecules. So if this is not 6 times what this is, then we've got not necessarily a problem, but we're going to run into an inequality where we have more of a certain substance. So if you plug that in, 0.13321 times 6, you actually don't get this exact number. You get 0.79926, which is less than this number. So that means we have enough water to make all of this react. So water is not the limiting factor. Aluminum sulfide is the limiting factor, because we only have enough aluminum sulfide. Well, we only have this much. We don't have any more than that. That's all we have. But we have more than enough H2O. So our plus minus here, it's not going to be the full amount. It's only going to be 0.79926. That's all that can react, because that's as much as we have here. But all of this will react. So that's going to lose that much material, and this is going to lose all the material. 3, 3, 2, 1. So basically what that means is that we're going to have some leftover water, and that's fine. You know, of all the things to have left over, a little bit of water is probably all right. From then, how much aluminum hydroxide do we have in the beginning, and how much hydrogen sulfide do we have in the beginning? Well, if you think about it, the reaction hasn't happened yet. So obviously we don't have any of that stuff in the beginning. We need to find out how much we have, how much it's going to gain of each one of these. That's where this ratio comes in again, because we know that all of this aluminum sulfide is getting reacted. So that we know it's going to be 0 at the end. We'll figure that out later, as much water as we'll have left. But we know that this ratio is going to work. So we know that if we have one of these, it's going to create 2 of those. So 0.13321 times 2 will give us, that's going to go up 0.26642 amount of aluminum hydroxide. So that's how much that's going to go up, and that's how much we're going to be left with of that. We know that that's how many moles of that particular molecule we're going to have. This one, the hydrogen sulfide, we've got 3 of those with only 1 of the aluminum sulfide. So whenever the aluminum sulfide reacts, we should get 3 times as many as that. So that's going to go up 0.39963 moles of hydrogen sulfide. And that'll be how much we have left there. Two. So, I mean, we're basically done at that point, but, well, we do need to figure this out. If we subtract the 0.79926 from the 1.1099, we know exactly how many moles of water we will have left, which is 0.31064 mole. And I'm playing it pretty loose with the significant figures throughout this. You know, obviously you'd want to, at the end, figure out how many significant figures you're trying to round to, and round to that at the end, you know, but, you know, play it pretty loose throughout. You just want to have enough to where you know that whenever you round it, you're going to get exact numbers and not, you know, not some abbreviated thing that doesn't make any sense, or this just not as precise as it could be. So let's say that we want to know, let's see, what would we want to know? We want to know exactly how much of this materials we're creating. So we've got the mole measurement, but I mean, if you tell somebody I've got 0.39963 mole of hydrogen sulfide, they're not going to know what the heck you're talking about. So you need to convert that back into a gram form, okay? That way you can say, oh, well, we produced this many grams of this, and we produced this many grams of that. In order to do that, you use that same conversion that you used earlier, but backwards. So how many grams of aluminum hydroxide did we create? Well, let's find out. We've got 0.26642 mole. This time we're going to put mole down here at the bottom so that we can get grams whenever we finish. And we know, well, we don't know because we haven't figured it out yet, but I can tell you I have figured it out, and you can use the same method to figure out the atomic mass weight of this particular molecule. And if you go the 0.26642 times 78.01, which is the atomic mass unit of that, but it's also grams per mole because they just translate so well, which is super convenient. You get 20.78 grams. So you have produced 20.78 grams of aluminum hydroxide. Then we want to know how much we've got of the hydrogen sulfide. So 0.39963 times 34.08 grams per mole of that molecule, and you get 13.62 grams of hydrogen sulfide. So now we know exactly how much we've produced, but like here's the thing, whenever it comes, and you could also figure out exactly how much waste you have of water left over. It is the exact same conversion. You know, you just do it that way, and you can figure out exactly what this number is equivalent to. That is not what we're going to do right now, because there's one more thing that you need to know about an experiment like this. Is most of the time you're not going to get these theoretical, pure, perfect results. A lot of times you're going to end up with a little bit less. Let's say that theoretically you wanted to create 20.78 grams of aluminum hydroxide, but you were only able to create 16.70 grams. For whatever reason, you know, like your experiment, I don't know, maybe your beginning materials just weren't pure enough. Like there's a few reasons that it could be as to why your experiment didn't produce the perfect theoretical results, but it never does. It will never create more than your theoretical, but it will always create a little bit less. So if we only created that much, you can figure out a thing called the percent yield, which is just simple fractions. If you wanted to create 20.78, that was your perfect amount but you only created 16.70, then you can figure out exactly what your amount is. And I don't have a calculator right here, but basically you divide your actual result by the theoretical result, multiply it by 100. It'll give you some percentage that will tell you exactly what your percent yield was. And then if you conduct the experiment in exactly the same way, you will get that percentage yield. And if it's not what you want, then you go back and you oh, I didn't realize you couldn't see the bottom of the page there. But yeah, that is the formula for figuring out the percent yield. And so basically, if it wasn't good enough, if it just you feel like you could do better, then you go back and you duplicate the experiment. Do it with better starting materials. Do it with cleaner equipment. You know, whatever it takes. That's what you do, and that's how you do chemistry.